We're going to use definite integrals to find the arc length of curves and the areas of surfaces of revolution. So we've already talked about the volume of surfaces of revolution. In this case, we're going to talk about how to find the surface area. To calculate the length of an arc or a segment of a curve, we're going to do this by straight line segments whose lengths are given by the distance formula. And the distance formula is one that you should be familiar with. It is d equals the square root of x2 minus x1 squared plus y2 minus y1 squared, where x1, y1 and x2, y2 are ordered pairs, coordinates for two different points. And a rectifiable curve, which is the type that we are going to be looking at, is one that has a finite arc length. It's measurable. So if you were doing this, just practically speaking, you might take a string and cut it along the curve and then measure the string. But we want to be able to do it in a little bit more sophisticated manner using calculus. So basically, you can think of all these little disjointed line segments, and if you were to approximate their length and add them up together, you would have approximately the length of the curve. So if we divide it into approximately n line segments and we sum up their distances, and doing a bit of algebra, we would get that the sum would be approximately the sum from 1 to n of the square root of 1 plus delta yi over delta x of I squared times delta x of I, given if we were to divide up in this manner using delta x of i's for our change in horizontal distance and delta y sub I for our change in vertical distance. And for the mean value theorem, it tells us that for some c sub I in each line segment, this ratio here is equal to f prime of c sub I. So if we imagine that we have infinitely many rectangles, turning this into a limit, which makes an integral, the arc length can be calculated by finding the integral from a to b of the square root of 1 plus f prime of x squared dx. So this is approximately dx, and then this is the f prime of x dx. And you can do the same thing for a function that's solved for y. So when you would know to do one or the other, if you had a function like y equals x squared, you're going to want to use the first version, but if you had a function like x equals y squared, you would want to use the second version. So let's look at an example. I have y equals x cubed over 6 plus 1 over 2x, and I'm going to write this as 1/6 x cubed plus 1/2 x to the negative 1 power, just bringing this up in the numerator because that makes it a little bit more easy to work with. So for this one, I know I'm going to need f prime of x, or y prime, which is the same thing here. So that's going to be, bring down the 3, and I have 3/6 x squared plus 1/2 times negative 1 x to the negative 2, or 1/2 x squared minus 1/2 x to the negative 2 power. So my s, which is the integral from a to b of the square root of 1 plus f prime of x squared, will be the integral from, let's look at our graph, this goes from 1 to 2 of the square root of 1 plus, let's go ahead and write this as 1/2 x squared minus 1 over 2x squared squared. And all it's going to take from here on out is some calculus and some algebra. So I'm going to go ahead and FOIL out what I need to FOIL out. So I'll have 1 plus 1/4 x to the 4th plus 2 times 1/2 x squared times negative 1 over 2x squared plus 1 over 4x to the 4th. When I FOIL that out, and you can see a lot of stuff is going to cancel. So here I can go ahead and cancel this 2, I can cancel this x squared. I get the integral from 1 to 2 of the square root of 1 plus 1/4 x to the 4th. This is going to be minus 1/2 plus 1/4 x to the 4th. 1 over 4x to the 4th dx. Now I can combine my like terms. I have 1 minus 1/2, which is 1/2, plus 1/4 x to the fourth plus 1 over 4x to the fourth. And I'm going to factor a 1/4 out of that, which will leave me with 2 plus x to the fourth plus 1 over x to the fourth dx. And then I'm going to bring out the square root of 1/4, which is just 1/2 times the integral from 1 to 2 of the square root of x to the fourth plus 2 plus 1 over x to the fourth dx. Now here's where we have to perform a little trick, because this x to the fourth plus 2 plus 1 over x to the fourth is secretly a perfect square. If we were to multiply by x squared times 1 over x squared here, we would have our a squared plus 2ab plus b squared format, which we know turns into a plus b squared. Here our a is x squared and our b is 1 over x squared. So this is x squared plus 1 over x squared squared. So I'm going to replace that in my integral. We're just being clever with algebra. And since I'm taking the square root, I can remove the squared, cancel out the square root and the squared, which leaves me with x squared plus 1 over x squared. And I can write that 1 over x squared as x to the negative 2 power. Now this is pretty easy to take the integral of. We'd have x cubed over 3 minus x to the negative 1, all from 1 to 2. And that's x cubed over 3 minus 1 over x. So I'll have 2 cubed over 3, which is 8/3, minus 1/2, minus 1/3 minus 1. And if you do all of the arithmetic here, you get 17/12 units. Now this is not cubic units, this is just units, because it is just a length measurement, but that would be your answer. Again, we're finding the arc length of this line segment here. So my y is 2x to the 3/2 plus 3, and you can see our graph goes from x equals 0 to, this is going to be x equals 8. Or no, x equals 9 actually. It's implied, it's not exactly said here. I will be very clear about what I expect your bounds to be in a test. So we're going to go to x equals 9. But for our f prime of x, we will have y prime, which is 2 times 3/2 times x to the 1/2 power plus 0, or 3 square root of x. So s will be the integral from a to b of the square root of 1 plus f prime of x squared dx, which is the integral from 0 to 9 of the square root of 1 plus 3 square root of x squared. So this will be the integral from 0 to 9 of the square root of 1 plus 9x dx. And our u here would be 1 plus 9x, so u prime is 9. So we need a 9 and a 1/9. So this gives me 1/9 times the integral from 0 to 9 of u to the 1/2 power du. And those bounds are on x, not on u. So that's u to the 3/2 over 3/2. Or another way to write that would be 2 over 27 times u, which is 1 plus 9x to the 3/2 power from 0 to 9. So I'm going to have 2 over 27. We'll have 1 plus 9 times 9 to the 3/2 minus 1 plus 9 times 0 to the 3/2, which gives me 2 over 27 times 1 plus 81 is 82 to the 3/2 power minus 1 to the 3/2 power. There's no real nice way to write this. I can go ahead and make anything to the 3/2 power is that number times the square root of that number. It's not really better, but you could leave it there. Or if you like, you can bring that 2 in and have 164 square root of 82 minus 2 all divided by 27. Either one's fine, but that would be my final answer.